So my name is Jason Nucciarone. I am a student in the Penn State College of IST, and I just wanted to say thank you for coming to my poster presentation. Now let's get into it. So, first place I want to start is with the background, and so starting from the beginning, about 10 years ago, there was a lot of research that started going into this field of adversarial machine learning, where machine learning models, specifically deep learning models, had this inherent vulnerability to seemingly undetectable inputs, even inputs that could not be recognized with the human eye. And so, just kind of giving a very top-level broad definition of specifically what my research and my co-contributors' research is looking into, kind of how we can create this marriage between, current adversarial machine learning research practices, which is using Jupyter Notebook and a lot of external libraries, and the software development practice of pipelines, and then lastly, kind of unifying with high-performance computing resources such as like multiple computing nodes and GPUs. And so now moving on here, I want to go specifically into the methodology and implementation of our work. And so really what we tried to create was a framework that really automated and kind of this plugin based automated framework that allowed users to researchers to quickly and efficiently spin up their own adversarial machine learning simulations. So once again, I'll draw your attention to this diagram here. This gives a nice outline of kind of how our framework works, starting with the plugins and user-specified parameters. So if you see here, we have these, user-specified hyperparameters. So that's kind of directives, external variables that users can set for their machine learning models, specifically like, what's the learning rate, what's the batch size, and then we have these plugins. So for plugins, we have these 4 subdivisions, so kind of going down the list. So we have data manipulation. So for those plugins, you could do things like dimensionality reduction, trend extraction, anonymization, and then we have training plugins, which you can use libraries such as TensorFlow, Keras. There are a couple other ones, scikit-learn, PyTorch, and then we have the attack stage. So with that, you could implement your own attack algorithms, or you could use currently existing attack algorithms that are provided by toolboxes such as Fullbox or IBM's adversarial robustness toolbox. And then lastly, we have this plotting and analysis plugin, which is automating the generation of graphs and data. So kind of, moving down the list here, so now we started with our plugins and hyperparameters. The way that users interact with our framework is by using these essentially XML control files, which is a schema that outlines the parameters and the rules for how the simulation operates. And then as you see here, we also have this global defaults file, which that essentially just kind of provides directions when they're omitted by users in the XML file. So then once the user essentially passes the XML file through the framework, this is where the magic really begins. So we start with the data manipulation and training stage. So what our framework does is it essentially uses OpenMPI to enlist the help of multiple computing nodes on a cluster to parse and then train data at a very efficient pace. So basically splitting all these tasks. And so the data is manipulated. So once again, like dimensionality reduction, and then like model training, the models are trained on that data. And then after the training is complete, we then move to this deployed model attack stage. So this is when common attack algorithms or your own attack algorithms could be implemented. So for example, in our work, we use the Carlini-Wagner L2 norm attack on our models. And so that's kind of where then the models are then loaded back into memory, and then the attacks do their work. And then once the attacks are completed, we then go into this plotting and analysis stage, where essentially we assess the adversarial robustness of our models, which what that typically means is like how well did it perform while it was under attack. And then once we have all that data collected, all the models saved, all the attack output log saved, we then create this compressed zip file, which then can be transferred off of a high performance cluster onto a personal computer, and then that data can be used for further analysis. So just kind of jumping into our initial performance results, they've been very promising. So we've kind of completed most of the Python libraries needed for the framework to be functional, in the sense that users can create their own plugins, as well as being able to install our framework on a high performance computer and being able to start working with it. We're also able to correctly spin up simulations using these XML control files, and then we've also had success using a high-performance computer that's located at the university where this work was done, which was Florida International University. And then if you kind of see here, we have these graphs, stimulation time statistics. So with the graphs, it's just an example of the kind of data that can be generated by Jespipe without really any kind of user intervention during the pipeline runtime. And so we have, for example, the first graph is adversarial robustness, and then the other one is comparing kind of the root mean squared against the mean absolute error. And then we also have like a way to kind of assess like, which algorithm, like which model, which manipulation is the best for, like, allows the model to be the most accurate. And then we have some simulation completion time statistics. So as we've discovered, adversarial examples take a very long time to generate. So 6-hour completion time, which is typically better than if you're just doing like single task, single instruction. So we're using that inherent parallelization. And then we're also able to train a very large amount of models in a very short amount of time. And then just kind of the wrap up here, we want to jump into the current identified limitations that we found with our work, and then kind of the future work we want to use to build off of this. So the biggest limitation right now is how efficient the user plugins are. So if users decide to implement their own algorithms instead of using something that was created by another user, typically that can add a lot of time onto the overall runtime of our framework. And so we're kind of thinking right now, well, what are ways that we could potentially encourage users to be a little bit more efficient, provide more statistics so users can see what the hang-up is. And then also, kind of for initial development, we only use like 8 computing nodes. So we want to be able to, within our future work, now jumping into the future work, we want to be able to expand the total amount of nodes that our framework is able to use on a supercomputer. And then just kind of some other future work things, a lot of these things are quality of life updates. So we have better error handling. So with that would include better help messages. So if like a user encounters an error, it gives a helpful hint for how to deal with it. We also want to have an XML validator. So if a user accidentally leaves out like a tag in their XML file, it lets them know and says how to fix it. And then just kind of some other features that we want to add. We want to have support to use other languages with our framework. So right now we primarily only use it in Python, but we want to see about incorporating like languages like R or Julia or even Java to do some model training and potentially attacks. And then just, lastly, as I had stated before, we want to be able to have even more nodes available to us. So instead of using like 8 computing nodes, we want to see what happens if we try and use like 200 computing nodes. So, yep. And with that, that's the end of my poster presentation. I know I'm about 3 minutes over here, but I do appreciate you taking the time to stop by. Have a great day. Thank you.